Okay. I'd like to go to the presentation from last time just very briefly because there's some new students who just joined the class. And very quickly, if you go to Sakai, you will see the portal. Right, the portal, and from the portal, you would get to the. This is the a screenshot of the portal, and this is the daily lecture summary. And so when you get in there, you would see this this file here, this Google Doc. Okay, and let me begin with this presentation so that everyone is right at the beginning of the course would be aware of the way my teaching style. Okay, the best is not to take notes. I'll take a few notes because I spend a lot of time type up my notes. So there's really no need to transfer the notes from my notes into your notebook, right? That's a futile exercise. Lecturers do their best work when students do not take notes. Why? Because connection comes from attention. And note-taking is inherently dividing attention. Okay? This is from an award-winning book, so please. Yes. And technology allows you to really focus on the discussion. Because when you take notes, you focus on not making mistake, and sometimes you cannot really, not making mistake or missing something. And most of the time, what I observe, and I will mention later. Okay, so avoid the furious scribbling, and also the use of technology would allow that. And if the class were more like a well-run meeting, where ideas were exchanged, and a defined outcome were achieved, that students would still need to take a few notes to follow the argument. Okay, so that's really the main point. And like I said, this is an award-winning book, and we'll have more. And this is a recent article in the Harvard magazine, and this is also interviewing Professor Eric Mazur, who obtained the Nobel Prize in Education that has $500,000. But really $500,000 is not wasted on something that did not create something revolutionary. Lectures are a way of transferring the instructor's lecture notes to students' notebooks without passing through the brains of either. Okay? Because actually, discussion takes more work from the instructor. Because if I have a hard copy notes, I just copy, and then you copy down my notes. It's really not much work. And while I write on the board, I was thinking about something else. And maybe the students wouldn't say that. That's what it means. How many of you know who Albert Camus is? He's a well-known, or was a well-known French writer and philosopher. And you see, this is a quotation, often quoted by Professor Mazur himself. Some people talk in their sleep. Lecturers talk while other people sleep. That's, and by the way, this link is live, and I post my presentation in the daily lecture summary. You can click at the link, read the article. It's very, very instructive. So, and here is another quotation from the article. The danger with lucid lectures, of which we have so many on this campus, that's the Harvard campus, with so many brilliant people, including Nobel Prize winners, is that they create the illusion of teaching for teachers and the illusion of learning for learners, students. Sitting passively and taking notes is not a way to learn. Yet lectures are 99% of how we teach. This is from 2012. Okay. So here is what I would advise a class to do. The best is to print out my lecture notes into hard copy. So you can follow my lectures and you can have a continuity. You know, when you have the hard copy note, you can take a few notes, just a few notes to follow the argument, because sometimes you need to write down something, okay, or to remind you of something. So print out my lecture notes, and it's available well before the lecture. And in fact, it has gone through several revisions. So it's pretty stable. You know, my set of lecture notes is pretty stable. And so you only need to take a few notes. So I may require to have hard copy of my lecture notes in class. Okay. In exchange, I would provide you with a free book. You don't even need to buy Crazy. This free book is given to me by a professor, so it's legal. Okay? So it's not. And so it's basically the equivalent of Crazy. Okay? So please print out my lecture notes. I think I will respond them. Okay. This is the second best, but like I said, having a hard copy is much better. If you have a tablet, you can display my lecture notes for continuity when I switch windows. You can use this now free program to take notes directly on the PDF, and you can even record the audio of the lectures. Okay, this is now free. It used to be not free. But like I said, you know, hard copy is much better. The advantage of this method is that your notes will be directly on the PDF, and the audio recording is also associated with certain pages of the PDF. It's a sophisticated program that I learned from, I mean, I did not use it, but I learned that a student in my class, actually in this course, exactly in this room, 2 semesters ago, in spring 2014, informed me about this. He actually used this program to write directly on the PDF and maybe record the audio. I don't know, but he did mention to me. This is not recommended, but you know, the laptop you can use, but you see the disadvantage of using the laptop to display my lecture notes is that you can take notes in your notebook, but you know, it's separated, 2 different objects, and you know, it's not that they are not associated with each other. So a month later, you know, it's hard to find, right? A year later, it's impossible. And so whatever you write directly on the hard copy or on the PDF will stay forever. Okay, so that's the advice. And so additional advice here, do follow my daily lecture summary document, which you saw there. Because if you wait for 2 weeks and only look at that and scurry and find where the lecture notes are to do the report problems, you will be overwhelmed. You could see my daily lecture summary from the previous semester, and you will see there's a lot of information in there. Okay, so please follow, read the lecture summary to be familiarized with it every day. Well, it is like my diary. I record in this diary all activities that occurred in class. Okay, that's my style. But you know, it's offered to you as a service. And if you don't like the way I organize, feel free to reorganize. You know, just by copying and pasting. It's very easy. You can do that. So you don't have to wait for me to do in whatever style, because everyone has different preferences. So, and this is the most flexible way to do it. Okay. So with that, I think, and by the way, my presentation lecture slides is listed here. So let me thanks here. This is S1 is slide Z1. That was the organization that I have here, I believe. Oh, this is a different code, sorry. This, but basically similar. This somehow I brought up. That was finite element analysis and design. This is IEA here. I teach finite element in the morning, but you see the organization is very similar. Chiefly for students who just came today and did not attend the lecture on Wednesday. Right, so it's the same. I believe that I have gone through all of this on Wednesday. And like I said, you have the video recorded here, and also the my handwritten note. Okay, so let's click here. You remember there was a problem, right? There was a problem with the stylus. It's now fixed, but when I went back, I rewrite this. So you see, this is an advantage of the way I function. When I write on the computer tablet, I often go back and annotate, and you can look at my handwritten notes from last semester. I don't write a lot in class, basically formulas, or even if I wrote on the board, it's the same thing. But when I went back, I added what I said in class, which students do not take notes, and that's half of the important information, So taking notes, not only that is not perfect, cannot be perfect, right? But let me do the job, and you can get everything that I said. That's even better. While in the meantime, focus on understanding the material, discussing, that's much better. Okay? Asking questions that would improve the understanding rather than just the futile transfer of notes from my notes into your notes. Why do that? I already did the work. So here, as you see, let me see, I should be able to get down. Oh, perhaps I need to go to high. Yeah, so you see, is Parker here? Parker was the student who mentioned Taylor series last time. So I noted down his name for active learning credits, and together with Robbie, right? Robbie is sitting, right?
Robbie.
Is it
Robert.
Is it correct? The spelling? How do you spell your name?
R-O-B-E-R-T.
R-E?
Or R-O-B-E-R-T.
R-O-B-E.
Robert.
Oh, Robert. Somehow I. Okay. Yeah, later I have a. Once I form teams, I will put the team number on. Okay, so I talked about the handwritten note, the video. You can just click at the video. If you use Google Chrome, there will be no problem. And the audio also. So it's, today I can record the audio of this lecture. So if you use Google Chrome, I use the format OGG, which is an open source format equivalent to the WAV format, which is proprietary. And if you use Google Chrome, you can listen without having to install anything. Okay. So the structure of my daily summary, you see that it's very consistent. Okay. At the beginning, these are the points that reminds me to tell the class. For example, fill out the team formation survey that I email out to the class. I mentioned about maybe I have also a tool that help to focus the attention to certain point that I'm talking about. Okay, so this is a convention that I use the green color. At the end of the class, I will highlight the portion in the lecture notes that I talk about in the class. And the magenta background color would be what I already discussed, presented in the previous lecture. Okay? And then the yellow background color would be important points to remember. I already talked about handwritten notes. Okay, so let's start with this motivation. This is, as I mentioned, this is, if you recall, from this, right? I use a real-world problem to motivate the learning of the method in the class, and there's a discovery of Neptune, but what I'd like to show today is the Akashi-Keiko Bridge, the longest expansion bridge in the world, to motivate the first half of the semester on solving system of second order ODEs, okay, vibration, essentially. All right, so let's look at that. I have the link here. I don't want to show the whole video, it's very long. So I just want to pick out certain portions of the introduction. Let me again put this on. The introduction would be from time 0 to 1 minute 25, and then I skip to the end, okay? And I'd like to keep in mind the following. Yeah, so let me boldface the important keywords here. What you want to keep in mind would be dynamics, vibration, damping, periodic loading. So all of these would be concepts that would be presented and how to solve problems that would model these mechanical phenomena. So that's the okay. So one, let me see. I hope let me start. Let me make sure that the sound is okay.
Is the world's longest suspension bridge. It spans a waterway 4 kilometers wide and is designed to withstand powerful typhoons, tsunami, and earthquakes. It is the pinnacle of bridge engineering. The Akashi Bridge owes its success to 7 key inventions found in these 7 landmark bridges. At the heart of each bridge lies a major technological innovation that allowed engineers to span ever wider chasms. One by one, traveling up the scale, we'll reveal the incredible stories behind these structures and the inventions that allowed them to grow ever longer. 7 ingenious leaps forward that enabled bridges to evolve from big to bigger into the world's biggest.
So now I skip to, you know, this is the link. You can look at this video, very nice, but I don't want to show the whole video as I mentioned, so I skip to time 37:45 to 49, 37:45.
Then, they must now be designed to resist a particularly destructive force of nature, wind. In 1940, a new bridge opens across the Tacoma Narrows in Washington state. But it has a fatal flaw. In a modest wind, the deck begins to move up and down, Then it starts to twist. Finally, the bridge collapses. Engineers now understand why the structure failed.
Aerodynamic instability has to do with the shape of the structure that the wind encounters as it blows across the bridge.
A bridge deck with a flat side presents an obstacle to the wind. When a crosswind hits it, the flow of air is disturbed, causing eddies to form above and below the deck. These produce areas of varying pressures that either suck the deck up or push it down. Once the deck moves, the bridge flexes against it.
The wind and the structure's movement actually interact with each other. It becomes a self-exciting phenomenon. It will build up the amplitude to the point where it will wreck itself, just as the Tacoma Arrows did.
One solution is to introduce a more streamlined profile to the sides of the deck to slice through the wind and channel it harmlessly over and under the roadway. In 1946, engineers considered using such a design for a new, even longer bridge. They have to span the 1.6-kilometer wide entrance to New York Harbor across the Verrazano Narrows. They expect the crossing to be so busy that the bridge must be able to accommodate 12 lanes of traffic split across 2 decks. But the engineers know that streamlined edges on a double deck might not channel the wind safely away. Instead, the streamlining could cause the currents of air to collide and produce further disruption. So rather than deflect the wind, they decide to resist it by stiffening the deck so that it can't twist or bend. The most effective way to do this is to enclose the decks in a great box. But they know a 2-kilometer long steel box would be too heavy for the bridge's cables. Instead, they take thin steel bars and assemble them into a lightweight skeletal unit. 75 of these lock together to form a massive open latticework of steel. This allows the wind to flow unimpeded through the structure. This unique design resists the powerful Atlantic storms and supports 12 lanes of traffic. Its twin decks carry almost 200,000 vehicles a day from Brooklyn and Queens to Staten Island and on to the main Atlantic highway system.
It's a remarkable achievement. This bridge supports 70% more load than the Golden Gate Bridge, which of course was its nearest equivalent at the time.
When completed in 1964, the Verrazano Narrows Bridge becomes the longest and heaviest suspension bridge in the world. The bridge marks the gateway to New York Harbor and stands today as one of the city's landmark structures.
Verrazano Narrows Bridge, I think, is the culmination of a great era of American bridge building. And of course, the biggest and the greatest of them all.
And the design is so good that over 30 years later, the Japanese used the same open box concept to stiffen the deck of their Akashi Bridge.
I'm standing at the moment within the stiffening girder of the bridge. You can see it's primarily triangular in geometry, a lattice work of steel members. It's also very light, and the whole makes up a box structure, which is very difficult to twist.
But the Akashi Bridge faces another challenge. It stands in a notorious typhoon alley. Japanese engineers must ensure the Akashi Bridge can withstand the worst nature can throw at it. So they build one of the world's biggest wind tunnels to explore its design limits. Even at 100th scale, the model of the bridge measures 40 meters. Huge fans generate the equivalent of 300 km/h winds, so the engineers can test and refine their design.
By using wind tunnel test, the engineers were able to devise a structure which would both minimize the load generated by the wind and also be stiff enough to resist any loads which the wind would cause.
The wind tunnel tests suggest they need to deflect the wind as well as stiffen against it. So they insert a massive steel beam just below the roadway. When a strong crosswind hits the beam, it gets redirected upward through a grill in the deck, neutralizing its destructive effect. The 1,900-meter steel spine works with the reinforced deck to ensure the Akashi Bridge can withstand typhoon winds of up to 300 kilometers an hour. The Verrazzano's wind-defying capabilities enable bigger bridges to safely straddle increasingly exposed crossings. But to build the world's biggest suspension bridge, engineers must defeat a force of nature powerful enough to shake the structure's very foundations. Japan is situated in one of the world's most seismically active areas. In 1923, an earthquake devastates Tokyo, killing over 100,000 people. Hundreds of tremors hit the country every year. The unstable ground makes Japan the last place on Earth an engineer would choose to build the world's longest suspension bridge.
If the ground beneath a suspension bridge is shaken by an earthquake, we could, in the worst case, for example, get a tower toppling over, obviously a catastrophic event.
The first line of defense against an earthquake is the bridge towers themselves. They're built from steel to make them flexible. If a tremor hits, the steel towers can move with the earth to absorb the shock. And inside each tower lies a second layer of protection, 20 huge pendulums called dampeners. Each 10-ton dampener hangs from a frame. If a tremor causes the tower to lurch one way, the huge hydraulic dampeners swing in the opposite direction, counteract the shift, and prevent the tower from falling over.
Now in these two models, we can compare the effect of fitting a damper. The tower on the left is a normal tower with no damper. The one on the right has a damper fitted to the top. And we can see how much each one sways by observing the arrows at the back. It becomes clear from this model test that the tower without the damper on the left is swaying more than the tower with the damper on the right.
To test the dampeners in the absence of an earthquake, engineers resort to a novel approach. They carefully choreograph 100 workers to sway in perfect harmony to mimic a tremor. During this man-made quake, the dampeners react to keep the tower steady. But on January the 17th, 1995, nature tests the technology for real. A magnitude 7 earthquake devastates Kobe, the city on the Akashi Bridge's north bank. It kills over 6,000 people and destroys more than 100,000 buildings. But the Akashi Bridge survives, saved by its dampness. It still bears the scar of that fateful day. The earthquake opens a fault line in the seabed directly under the bridge. This causes the ground and bridge towers to shift apart and stretches the bridge by over a meter. Engineers must fill this space with extra decking to join it to the shoreline.
As a result of this earthquake, the longest bridge in the world became a little bit longer.
That's really all I want to show. You see very beautiful work that survived important, strong earthquakes. Remember when the workers do like this? That's periodic excitation, right? Damping. So all of these concepts you will learn in the first half of the semester. And like I said, the techniques that you learn applies to real-world industrial problems, that can scale up to millions of degrees of freedom. Meaning, system with couple that has millions of equations. Okay? Not just 2 equations that we use. But like I said, we use 2 equations because one has to learn to walk before one can run. Right? So that's the reason. But let me mention the following. When I said try not to take notes or take few notes in class, I do watch the students, and I noticed that some were not so convinced, and I really thank that student for making that body language. But that also reminds me to tell the class the following. I never said to learn math or mechanics that one does not write at all. No, I never said that. What I meant is, don't do that in class. Do that at home. If you want to rewrite my notes, which I do advise, please do so at your own time, when you want, where you want, however long you want to take. You need to do that, right? You cannot learn math or mathematics or mechanics without writing, no. And what are the opportunities to do that? When you solve the problems, or better yet, right after class, okay? So I hope that with that, we all agree that, you do need writing, but try not to do in class because you want to focus on the content. Okay? So here's the link to the first set of lecture notes that I want to discuss. Okay, so here you see what I wrote here is, let me bring up the mask. Okay, so here is the complete content of the section 53B. Don't worry about the number, because these are the numbers that I use for different topics. So if you compare to the daily lecture summary of last semester, spring 2014, you see that it would be much shorter at the beginning because I was developing the notes and I add, more and more. So this is like the state of the lecture summary at the end of the semester, or after I have completed explaining section 53B. Okay, so that's just to give you a heads up. And now I will bring up my lecture notes on Sumatra PDF. Let's see, 53B right here. Okay, usually what I do is I would have three windows. And this is just to help you to see. Should be able to. Oh, this is wrong. the new version, you know, the old version allow me to I prefer several copies. This is probably I need to see how I could cope with this, but let's see. Yeah, I can write on. So I use a combination of the Smart Ink that I can write on the PDF, but without keeping the result. You know, this is just to make some points. And for example, you have seen the Tacoma Narrows Bridge collapse in the video, and so what we will focus now is directly in the multiple degrees of freedom system with 2 degrees of freedom. It's a system of spring mass and damper system that you were motivated through the Akashi Keiko bridge. Okay? And so let's go to that immediately. I may come back to this if needed later, but here I would like to focus just to mention a few words about this. The collapse of the Tacoma Narrows Bridge is not due to resonance. That was an error that is often made. You know, if you look into the web and you look at the video, sometimes they mention this, and even in many textbooks. So don't believe anything that is on the web. Certain textbooks even did not provide a complete or correct explanation. But I don't have time to get into this. I teach this in more detail in my finite element course. So now I'd like to present this. Okay, you know, you can do a mental experiment yourself, right? How long does it take time to draw this figure on the board and then transfer to your notes? Right? And how about colors? Okay. So I hope that you would be convinced. Okay. So 2 degrees of freedom. What is a degree of freedom? Essentially, the displacement of a mass. So this is, you have 2 masses. Each mass has a displacement represented by this green arrow here and denoted by D sub 1. D is mnemonic for displacement, and 1 is because that's the first displacement degree of freedom associated with mass M1. For mass M2, you have the displacement degree of freedom D2. And T is the independent variable. Yeah, maybe I can also use this to help focus what I'm talking. Right? So T is the independent variable representing time, and this is just to mention that these are functions in time. Okay? Now, on mass M1 and M2, you can also have applied force. Remember the workers, when they move back and forth, that's the application of periodic loading. So here, the applied force, cap F1 and cap F2, can be also time dependent. Right? A periodic function is an example of a time dependent function. It's a particular case. Okay? Now, so let's go in slowly. So I basically explain what it means by a degree of freedom. Okay, the applied force. So now let's look at the structure of this system. Right, A, B, C, D are called the nodes. That's the terminology that is used often in finite element. You have nodes and element. So here you have element 1, element 2, element 3. Element 1 goes from node A to node B. Element 2 goes from node B to node C. And element 3 goes from node C to node D. So now zoom in further in detail. What are the sub-elements of element 1, 2, and 3? Right? So you look at element 1, for example. You see that it has two components, a spring and a dashpot, right, in parallel. And you can also have things in series. So here you have a parallel spring and dashpot or damper. And then you have a mass M1, the same system, but not necessarily with the same numerical coefficient. So therefore, the variable K2 and C2 are used to designate that these are the spring constants and the damping constant associated with element 2. Okay? And likewise for element 2. So you have element 1, mass M1, element 2, mass M2, element 3, all in series. How about the boundary conditions? At A and at D, in this particular example, they are fixed. Okay, meaning the displacement would be 0. Yes, please.
What are C1, C2, and C3 again, please?
Okay. C1, C2, and C3 are the damping coefficients, right? They are the equivalent of the spring constant. Okay, so this is the damping coefficient. Basically, that represents the property of the viscous damper. You know, everyone knows the meaning of the spring. Well, I say everyone, but let's ask the critical thinking question in the review. So could someone in the class explain to the class how do you use, or let's say, how do you express or define the spring constant? Okay, what is your name?
Kyle.
Kai, yeah. So Kai, can you mention something that would define the meaning of the spring constant?
What's the resistance to a change in length?
Yeah. So what in terms of equation, how do you write the equation? Let's say the force, and then you have displacement, right?
So you have force equals K times your
Right,
displacement.
very good. So this is Kai. So let me quickly note this down so that you have in your notes. So essentially what Kyle said is F equal to K, and if we call D the displacement of F equal to KD, right? So that's how about the damper? How do you and let's write F sub K here, or if you want you can also write F sub S from here, you know, with S representing the spring, you know. Yeah, and so really just, but how about F sub C for the damper? Anyone in the class?
Oh, yeah.
Yes.
I think it prevents it from oscillating. If you have like some sort of spring and it's like going back and forth, it won't slow it down so it stops moving back and forth.
What is your name?
Derek.
Derek?
Yeah.
Yeah. You know, my question is, how do you define the damping coefficient, right? So it should be, this is a hint, very similar to the definition of the spring constant. Okay, and this is viscous damper. So, so the definition is that you have the c times the velocity. Okay, this is the velocity. D dot means the derivative of d with respect to time t. Okay, so you write. Let me write the definition. And this is an unfortunate choice of notation. Okay, because d we use as displacement, but d is also used in the Leibniz notation for derivative. Okay. So d dot. Yeah. So let me use different color. So that's the that's another advantage of using this tool, is that I can use different color. Okay, so this is velocity. Whereas D here is displacement. You know, for now I just quickly like this. by the way, this is need not be constant, okay? It can be a function of time. So let me emphasize, and you see, I can change easily. And so here I put time in to emphasize that all of this is really time dependent quantities, okay? Not constant. And even d dot is also a function of time. Okay? So that's, I hope everything. Thank you. 5 minutes. Okay, so let's let's try to move forward. So I have introduced all of the elements there, and the let's see. Let me clear the thing here. When you have teams, you know, Derek, I remember Derek asked me the question, what does it mean in class assignment? So part of the in-class assignment is interaction, discussion, but also write the team lecture summary at the end. But that is next week, you know, when I have formed teams. Okay. So all of these quantities have been introduced and defined. You know, the nodes, A, B, C, D, the elements 1, 2, 3. Between what nodes and what nodes, the spring constants, K1, K2, K3, the masses, 2 masses, M1, M2, the damping coefficients, C1, C2, C3. Oh, by the way, the spring constants and the damping coefficients and the masses are constant. Okay, in this example, they are not time varying. Can someone think of some mechanical system that has varying mass? Something that has
Something with a
mass that
tank or
is a function
something.
of time.
Space shuttle.
Yeah, or a rocket, right? Because fuel would be expanded, and so therefore it gets lighter and lighter as it goes on. We're not doing that. That's more. Okay, and then the applied forces. So how much time do I have here? 3 minutes. And please remind me of, I need to remember before I forget. And this is directly here. Kyle. Sorry, here you need to help me. Is it like this?
B-R-E-K.
B-E-R-E-K. B-E-R-E-K. One more. Someone please, if I forget, you know, if you do something in class, remind me, because sometimes I cannot. I thought there were 3.
The space shuttle answer?
Yeah, what's your name?
Nick.
Nick?
Yeah.
Right, thank you. Okay, let's see what's installed. Okay, so the next thing, okay, here, you know, how do you analyze a system? And before we quit, okay, let's say in statics, let's go back to statics, forget dynamic for now. In statics, you are given a structure. How do you analyze the structure? Free body diagrams, very good. What is your name?
Maria.
Now you need to have.
It's Maria, but with an E.
Yeah, we can talk after that. Please go. But here's what I want you to prepare mentally before the next class. Okay? In statics, when you want to analyze a system, not just free body diagram of the whole system, but also subsystems, right? You divide into subsystems, and then each subsystem has to be in equilibrium. So keep that in mind for next time.